Hello everyone, my name is Joscha Mueller. I'm a scientific engineering associate at the Lawrence Berkeley Lab, and today I will present you a Modelica library for continuous and discrete extremum seeking for static and dynamic systems. This paper was conducted together with my co-workers Maxime Baudet, Daniel Arnold, Michael Senko. And if you have any further questions after the presentation and after the question and answer, there's my email address. So you can shoot me an email if you want to know anything else. So to start, we are presenting the Modelica Extremum Seeking library, and it has continuous and discrete implementations of different extremum seeking controllers. And it also shows that it's suitable for different domains. So you can use it for mathematical problems, electrical problems, or like mechanical problems. So we will show a few examples of how you could use the extremum seeking models for your own applications. The motivation behind this library was that we did a lot of research around extremum seeking, and there hasn't been really any library containing different extremum seeking blocks for Modelica. So first we created models for Python and models for MATLAB, but we wanted to broaden the audience, so we wanted to also conduct the extremum seeking in Modelica, and has the advantage as it's an open source software, and it's very easy to reuse the models created in Modelica. And if people are not using Modelica, we also provided all the models as FMUs utilizing the FMI standard. So people can use the blocks in any kind of software which supports the FMI standard too. Here you can see the three different ES controller types we implemented into the library. At the top you see in red the conventional ES controller, below in green the single fixed step ES controller, and at the bottom in blue the multiple fixed step ES controller. So for the conventional ES controller, we have the set point here, which will get a probing signal added at this point. And the output of the ES controller then will go into the unknown system we test. And the output of that will go into our objective function. And the objective function will be fed back into the controller here. And then we have a bandpass filter built from a high-pass filter and a low-pass filter. And after that, we will have a demodulation of the input. So with that, we extract the original probing signal from the input, and then we will feed that into a low-pass filter, and then through an averaging operator, which average over one probing cycle, so that makes the output a little bit smoother, and the set point integration will be a little bit smoother based on that. And then we get into the gain, and then we have the integrator at the end, and then we start again at the beginning. So that's one cycle of the ES controller. Below the single fixed step ES controller, one difference is it doesn't have the initial second low-pass filter. The probing signal here is a sigmoid function, so that's different too. And therefore the demodulation is also the sigmoid function. And for the gain, we multiply the gain with a sigmoid function and the step size. So all the outputs always have to be the multiple of a certain step size, and we can only change the output by one step. And then we have a discrete integrator, and we have a zero order hold at the end. So the output will be held for a certain amount of time. And for the multiple fixed step ES controller at the bottom, it's the same as single fixed step ES controller, except that we have a rounding function here. So the gain will be rounded to the closest possible set point. To compare the three different ES types, we just use a simple quadratic function and try to optimize that. So the target we set is 1, and we simulated that in Modelica with the three different controller types. So the outputs of this little test show the differences between the different controllers. So in the first column, we have the continuous ES controller. In the second column, we have the single fixed step ES controller. And in the third column, we have the multiple fixed step ES controller. And the first row shows the set points. So you can see that the continuous ES controller is a very smooth function which slowly converges towards the target of 1. The single fixed step ES controller will always, in this case, the step size is 0.1, and it will increase at every iteration for the set point by 1 until it reaches 1, but then it will overshoot to 0.1 because it will always increase or decrease its output by 1 set point. It can't stay on 1 set point. So once it reaches 1, it will get to 1.1, and then it will go down to 1 again, and then it will go to 0.9. So this is one of the downsides of the single fixed step ES controller, that it will always change its set points. Whereas the multiple fixed step ES controller, you can see all the steps it does are a multiple of 0.12, but it can do multiple steps at a time, and because it's rounding to the closest set point, it in this case is able to round to 1 and then stay on the optimal target value. The second row shows the actual output of the ES controller. So this looks a little bit different than the set points because you see those waves around the set points, and this is related to the probing signal which is added to the output. So this is one downside of the ES controllers, that you will always have an additional probing signal on top of the optimum set point. And you can see the same for the single fixed step ES controller and the multiple fixed step ES controller, that it has those oscillations around the set point. The last row shows us the objective function, which shows that all of the controllers are able to converge to nearly 0. They will still probe around the optimal objective, but they nearly achieve it. So the next system we show you is a physical system, which is a mass spring damper system, and it's an extension of the Modelica mass spring damper model, which is already in the standard library included. And what we try here is to optimize the position of the mass. So we have a target value of 5. This is 5 meter, and we have the position sensor located here. And what it will do is we have the mass spring and the damper at the bottom, and it tries to set the force at the bottom left to an optimal value so that the distance from the connection point to the mass will be 5 meters. So the position value and the target value will go into the objective function, which will subtract the target from the position and then square this value, and that's the input for our ES controller. And the ES controller then will output its control signal and apply it to the force. So we control the force here, and let's look at the result. So we can see in the first diagram, it shows the force. The second diagram shows the mass position, and the third plot shows us the objective function. In the objective function, we can see that it at some point converges to 0. So it's able to optimize it. And we can see in the second diagram the target position. So the system has some initial inertia. That's why it's swinging around at the beginning a little bit stronger. Then it slowly moves to the controller can work and will slowly converge to the target. But you can see that in this example, it takes relatively long to converge to the optimal value. And this is because spring mass damper is a natural low-pass filter. So we have to apply low frequency, which takes longer to converge than probe with a higher frequency. So for this example, the ES controller is not ideal. You could use other controllers, but we wanted to show that you can control different kind of systems with the ES controller. Another physical example we use is the rolling wheel example. It's another extension of the Modelica standard library. And in this example, we have this rolling wheel, which has a mass of 1 kilogram. It has inertia of 1 kilogram square meter. And we apply a torque to the rolling wheel and want to optimize the speed. So we measure the speed and have this objective function, and the target is 1 meter per second. So it goes into the objective function. The speed, the target will be subtracted. We square the output of that, and this goes into. Here's a picture of the discrete ES multiple fixed step controller, but it will actually conduct this simulation with all 3 types of ES controllers we presented before, and it will control the torque which is applied to the wheel. So in these 3 plots, we will see the outputs of this simulation. So at the bottom again, we have the objective function. In blue, we see the multiple fixed step ES controller. In green, we see the single fixed step ES controller. And in red, we see the continuous ES controller. And we can see they all are able to reach the objective function, the objective optimum. And the first diagram shows the torque, and the second diagram shows the wheel speed. So we can also see how the controller changes torque, and then in response to that, how the wheel speed changes. And we can see that in this example, the multiple fixed step ES controller is slower than the other controllers, and it doesn't change its set point initially, and then that's based on the integrator still integrating slowly. Then it starts to integrate to a higher value quickly and overshoots, and then has to come back to the optimum value, overshoots towards the bottom again. So in this example, the other 2 controllers perform better. So again, shows you like the ups and downs of the different types of the ES controller. And the next example is a power system example. We have a distribution feeder with 9 distributed energy resources, which you can see here, and here, and here. And we have 6 different set points. So the optimization target here is to achieve certain power injections at the feeder head for active and reactive power. So we have 3 set points, one for each phase, and 1 for Q and 1 for P. And in this example, we utilize the 2D ES controllers we mentioned before. So the distributed energy resources can control their P output and Q output. Both have the same frequency, but they're shifted by 90 degrees, so their signals don't interfere with each other. Look at the results. We can see that all targets can be achieved. We reach the active power at each phase, and we reach the reactive power at each phase at the feeder head. So it shows that like many controllers together can like work on like one problem and are still able to optimize it. For our library, we mostly use the very generic design. So we just used mostly the basic standard library models from Modelica to model the different types of ES controllers we presented before. And we combined discrete and continuous models, which is one of the strengths of Modelica, that you can combine discrete and continuous time. And we have different example applications for the different domains, so everyone can see how you can use the different models. And finally, we also provide all the models as FMU blocks, so also non-Modelica users can use the Modelica Extremum Seeking library. Thank you for your attention. If there's any questions, there will be 5 minutes for a short question and answer.